Welcome to the lecture Introduction to Digital Archaeology, 3D Data Acquisition and Modeling. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Welcome to the world of virtual 3D models. With the right instructions and tools, anyone can create such models nowadays. We want to start with the following question and the result of this lecture. Why are virtual models an important tool in archaeology? It is obvious that 3D models as a virtual representation of reality should at least have the property of making things measurable. If things have run correctly during creation and the model is coherent in itself, by this is meant the relative relationship of the existing features, the knowledge of a real measured distance between two of these features is sufficient to correctly determine all other distances within the 3D model. In addition to distances, volumes can also be determined in 3D models. Thus, measurements of even large quantities of objects can be automated by an adequate good preparation of the 3D data in combination with the right methods. This could be very helpful, for example, for a statistical classification of objects. If another important aspect is added with georeferencing, we can even anchor the model with a real location in the world. Coordinates in the virtual model then correspond to real measured coordinates. 3D models are very popular as a visual result of a documentation campaign. Who doesn't like to show a detailed moving 3D model of an outstanding find, thus transporting the auditorium of a conference room into another temporal time period? This digital presentation with the comments and background of an expert, and we will come back to this in a moment, is enough for the auditorium. No one would expect to see the original artifact at a conference. Digital models are suitable for presenting results in publications. A common practice is to publish a 3D model on one of the major archaeological platforms. The German Archaeological Institute, for example, offers one of the largest archaeological databases with Arachne and has almost 5 million entries. A very interesting idea is certainly the use of pattern recognition methods directly on an excavation or during the exploration of a site. The ArchAid project, funded by the European Union with almost 2.5 million euros, had the aim of providing a platform for 3D models and metadata, and in parallel developing an app to match new finds on an excavation with those in the database, possibly enabling faster assignment and thus dating. A similar idea is being followed by University of Applied Sciences Dresden in cooperation with the German Archaeological Institute and the State Office for Archaeology in Saxony with the VOC tree analyzer software. It breaks down objects in the database into features and generates so-called unique fingerprints. This can later also be used to assign fragments of the learned information to known objects. The database currently focuses on the classification of medieval needles, which were provided for this purpose by the State Office for Archaeology in Saxony. With 3D models, we have a digital representation available that we can further process in various ways to make useful information visible. This example was taken during a documentation campaign in the Orkhon Valley in Mongolia in 2018. The representation of the terrain height in digital numerical form allows numerous mathematical manipulations to make even the finest structures visible in the model. In picture A, we see a pure aerial photograph with a section of about 1 square kilometer initially shows no signs of human settlement remains here. Image B shows a vegetation model which, however, also provides no indications. Only a false color representation of the 3D model in relation to the given height differences makes structures visible. Figure D shows an enlarged view of one of these structures. A measurement of the height course on a length of 30 meters shows here a difference in height of nearly 25 centimeters on 30 meters. This is not visible in the field as a human observer simply because of the vegetation. The symmetrical structure can now be indicated over an area of almost 1 hectare. The structure visualized in the original representation provides a starting point for further investigation. The case that archaeologists, for example from Europe, bring finds from their own excavations from distant countries back home and present them there in museums, which was all too common in the past, is politically more than questionable and has been history for a long time. In the past, this was either not publicly discussed or explained by the fact that the historically valuable finds were not safe in the country where they were found and were only transferred for protection. Nowadays, this practice is no longer part of the scientific standard of archaeological work. However, the question now is how archaeologically oriented museums will continue to operate in the future. Here, 3D models can provide an important alternative. With modern 3D printers, which now work with a wide variety of materials, 3D models can be quickly duplicated and printed in series. Virtual models, through the use of augmentative reality, can certainly be an interesting tool for the curator and experience for the visitor. Digitized finds can significantly speed up the scientific interpretation process by making it parallel. Unfortunately, however, this is only wishful thinking, which clearly contradicts the currently established nature of scientific work. Only after the digital find has been studied in depth and the results of the research have been successfully published, sometimes the digital finds are published as well. This is often because it costs a lot of money to create a digital find or reconstruct an area. There are hardly found examples where digitized finds were published first and own interpretation was renounced. As a rule, researchers feel forced to keep collected data under lock and key until they have published their interpretations of it in their own name. Recently, however, there has been a trend to also recognize the publication of data as a scientific achievement, which should significantly increase the motivation to do so in the mid-term. In recent years, 3D reconstructions have become established in archaeological documentation campaigns and are essential as a visualization or in presentations of results. In most cases, they are at the end of a documentation process chain. In the case of the examples from Mongolia, however, a 3D model often represents the beginning of a documentation campaign and was the basis for questions arising from it. Currently, there is also work in which the 3D model is placed in the center of the excavation documentation and is used, for example, for annotations, measurements, and localizations directly during the excavation. Which data acquisition techniques are typically used in archaeology? With computer tomography, or neutron tomography, and ground-penetrating radar, we have two non-invasive methods at our disposal with which objects can be transilluminated or the terrain examined on the basis of the reflection of electromagnetic waves without opening or damaging them. Computer tomography is used in medicine and uses X-rays to create cross-sectional images of the interior of objects. Thus, it allows non-invasive detection of the internal structure of objects. CT scanners are usually large stationary devices and their cost is very high. Similar to computed tomography, neutron tomography is based on acquiring a series of projection data taken from different angles. In contrast, however, neutron beams rather than X-rays are used. Neutrons have the ability to penetrate materials of varying density and composition and provide information about material properties. In archaeology, for example, the CT scan is used to examine mummified remains and analyze their internal structure without having to physically open them. A NT scan can be applied, for example, to the material composition of historical silver coins. Ground-penetrating radar offers another interesting technique that can reveal subsurface, non-visible structures. The operation of a georadar is based on the principle of reflection and absorption of electromagnetic waves. The device emits short electromagnetic pulses that penetrate the ground or material. These pulses are reflected or scattered at the interfaces between different materials. An interesting documentation project by the Norwegian Institute for Cultural Heritage Research, using a georadar from the Ludwig Boltzmann Institute for Archaeological Prospection and Virtual Archaeology in Austria, shows how the geo-referenced result provides information about structures located in the ground. The enlarged radar image shows a complete shipwreck from the Viking Age. Other methods, in which the object of interest is first excavated, opened or exposed, belong to the so-called invasive methods. These methods can only digitally reconstruct things that are visible. Laser scanning uses special devices that systematically scan the object's surface with the aid of laser beams. Here, for example, the scanning rate can be set via the distance. In structured light scanning, various structured light patterns are projected onto the object's surface and recorded by a camera. The surface structure can be derived from the projection pattern of the light stripes. In reflectance transformation imaging, several images are taken with different light source positions for a fixed camera. From this, the material properties can be derived with regard to the reflectance behavior. If this is combined with photogrammetry, for example, 3D models can be generated and displayed with different reflectance properties. In photogrammetry and videogrammetry, the object structure is derived from common visual features that can be seen from different camera shooting positions. Invasive methods also include reconstructive 3D modeling, in which the 3D shape of the object is reconstructed by hand in the same way as drawing. Laser scanning is a technique that uses a laser beam to scan the surfaces of objects or environments and create a point cloud of 3D coordinates. The system measures the time it takes for the laser beam to return to the surface and uses it to calculate the distance to each point. Repeatedly performing this process creates a dense network of points called a point cloud. It provides detailed information about the surface and enables the creation of high-resolution, accurate 3D models. The initial cost of a laser scanner is also typically very high. Large measuring devices must be transported and set up at various points. Airborne light detection and ranging works similarly to laser scanning, but uses pulsed laser beams instead of a continuous laser beam. By having the LiDAR sensor continuously sweep the laser beam in different directions, or by moving the sensor itself to scan, a dense network of measurement points can be generated. These point data are stored in a point cloud representing the spatial structure of the object or the environment. Compact mobile devices are already being used in the multicopter field. In archaeology, for example, LiDAR enables the recording of terrain shapes and topographic features, the identification of ground structures, and the creation of digital terrain models for excavation planning. It also provides a fast and accurate method for recording and documenting archaeological sites and landscapes. Here we see a terrain model of a settlement structure in the Amazon of Bolivia as an example. When scanning with structured light, patterns of light structures are projected onto the surface of an object using a projector, while a camera records these reflective patterns. By analyzing the deformation, the system can reconstruct the 3D geometry of the object. The cost of structured light scanners can vary greatly, but they are generally more expensive than conventional laser scanners, but less expensive than high-precision laser scanners. There are already mobile devices that can be used to scan objects fast. Scanning with structured light allows large areas to be scanned quickly and provides highly accurate 3D data that can be used in archaeology for the 3D reconstruction of objects. In this video, we see the use of a structured light scanner at the Saxon State Office for Archaeology. The surface structure can be derived from different light patterns and their reflection. There is already a wide variety of color and light patterns used in structured light scanners. Reflectance transformation imaging is a technique in which a series of images are taken at different illumination angles to analyze the reflectance properties of the object surface. In computer graphics, for example, the reflectance properties are measured with a Gonio Reflectometer and described in a BRDF. In this way, textures with special material properties can be generated very quickly. Thus, it represents an extension to photogrammetry and videogrammetry. While in classical photogrammetry the current reflectance properties of an object are baked in, and thus the objects usually appear dull, in RTI an individual reflectance pattern of the surface can be generated. This can make a significant difference in a subsequent 3D display with varying light sources and viewing positions. RTI is used in archaeology to reveal fine surface details of artifacts, inscriptions, and paintings, and to aid in deciphering and analyzing visual features. We won't go into detail here for now, but for those who are interested, a detailed description of how a Gonio Reflectometer works, what a BRDF exactly is, and how it revolutionized computer graphics can be found in my German textbook. Photogrammetry is based on the analysis of photographs to derive the spatial geometry of objects or environments. By analyzing common image features, 3D models can be created. If image selection algorithms are used, videos can also be used for 3D reconstruction. For this purpose, the photos relevant for the reconstruction are extracted from a video stream. Photogrammetry is widely used in archaeology to record surface details of objects, archaeological sites, and terrain features. Here we see an example of the royal tombs in Cyprus, captured with a simple smartphone and processed in reality capture. In the archaeological context, digital 3D models can be reconstructed by a person using digital tools based on excavation plans, drawings, historical descriptions or depictions, as well as analog finds. This is necessary, for example, when the model to be reconstructed no longer exists and historical knowledge and analogies of construction methods or craftsmanship lead to a digital reconstruction. This reconstruction may also change with new insights. As an example, here we see the result of a semi-automated 3D modeling using procedural methods to reconstruct the Great Hall north of the Erdene Zoo Monastery in Mongolia. A variety of tools can be used for reconstructive 3D modeling. SketchUp, Blender, or 3ds Max are popular. Classically, we count laser scanning, structured light scanning, reflectance transformation imaging, as well as photogrammetry and videogrammetry among the methods of 3D reconstruction. Here, the objectives of the reconstruction and the available equipment or finances must be clarified in advance. Photogrammetry or videogrammetry offers by far the simplest and cheapest access to this topic and can be used directly by anyone without major hardware and software requirements. All that is needed is a camera, which has become an essential part of everyday archaeological documentation anyway. Scanning with laser or structured light is ideal for archiving objects in museums, for example, because of its high precision. How can I further my education in the field of 3D documentation? If you are interested in the background of photogrammetry and videogrammetry, if you are looking for data packages and practical examples, if you are looking for solutions in case things don't go as planned with the reconstructions, then my book might be a good starting point for you. In addition to an introduction to the use of cameras and learning how to use multicopters, there are also aspects of underwater archaeology. You will also learn how to perform archaeological documentation with mini-submarines. Last but not least, we see that in addition to numerous data packages from the last 10 years of documentation, even a part of the Toro Farnese in Leipzig is being discussed. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own.